Hello, good day. So on this part of this video, I will be going to discuss with you about the basic concept related to geometric geodesy as preparation to geodetic control network. So as we proceed, let us first know what is a geodetic control network. So how is that geometric geodesy is related to geodetic control network? So ano ba natin magpagaintindi ng geodetic control network? So geodetic control networks, so often called natin na control network, geodetic control points, or reference points. So it's a network which are measured precisely by techniques of surveying and geodesy. So in that part pa lang, so a network pala is measured precisely by techniques of geodesy. So geodetic control networks provide us with control points given in the same reference system or coordinate system. So the positions or so-called coordinates of these points are determined using geodetic observations in an appropriate frame. So these geodetic observations include the branches of geodesy. So these control points are necessary for the definitions of coordinate system. So control networks are a set of control points covering a large region. So coordinate system. This coordinate system consists of two, which is horizontal coordinates and vertical coordinates. So these horizontal coordinates is coordinates in the surface, such like latitudes and longitudes of points, while on vertical coordinates naman is the distance between the points and the reference surface or the ellipsoidal height. So amin yung tatawag natin na 3D coordinate system. Now, paano sumulod ang geodesy? So first, recall natin, so geodesy is the discipline that deals with the measurements and representation of the Earth. So including its gravity field in a three-dimensional time or varying space. So on geodesy, so relies on trilateration, leveling, satellite observations, or gravimetric observations. So since nga geodetic control networks are points, reference points, so kailangan natin geometric, diba? Tatawag from the word geometric itself. So geometric geodesy is concerned with describing locations in terms of geometry. So yun na nga. Since an shape on Earth is an ellipsoidal, so diba there man a perfect square or a flat. So coordinate systems are one of the primary products of geometrical geodesy. So that's why geometric geodesy is very important before in preparation parahan geodetic control networks. So hope that you understand.
When beginning most surveying and mapping projects, you are trying to find the coordinates of an unknown point or points. So you need to start at a place where the coordinates are known. Such starting points are called your project control. Using project control that has coordinates from the National Spatial Reference System, or the NSRS, ensures consistency with other surveys and maps that also use the NSRS. So that when maps are created, property boundaries determined, and roads planned, everything matches up. For decades, surveyors relied primarily on passive control marks to tie into the NSRS. Passive control marks are usually some physical object, often a metal disc or rod installed in the ground. They are called passive because they can't alert you to their movement, and their coordinates may not be checked and updated for years or even decades. Over 800,000 passive control marks were set across the country, generally by the federal government, to build the NSRS. Over the years, however, many marks have been disturbed, damaged, or destroyed. The coordinates for many others are no longer valid due to earthquakes, subsidence, or other crustal motion. For these reasons, you should always check a mark's coordinates before using it as control, and there may not even be a valid mark in your area of interest. Today, instead of marks in the ground, people are using permanently installed Global Positioning System, GPS, and other Global Navigation Satellite Systems, GNSS, receivers as active control. These receivers are called active because they are always collecting satellite information which tells us if they have moved, and if so, how much. You can utilize active control by accessing data from a nationwide network of continuously operating GPS reference stations, or CORES, to compute an up-to-date position in the NSRS. CORES act as your known points to help you establish coordinates on unknown points. Each CORES includes a highly accurate receiver that constantly collects radio signals broadcast by GPS and other GNSS satellites, allowing the coordinates to remain up to date. NOAA works with many partners to manage a network of several thousand CORES, which are located in secure areas to ensure their longevity. CORES coordinates, accessed via the Internet, are validated daily and updated in the event of land movement. This is a very different approach than passive control, where coordinates may not be checked for years. Using passive control requires you to start your survey from an existing physical point, which you must find and occupy with surveying equipment. Conversely, users have no need to physically visit a CORES site, and in fact can use CORES from hundreds of kilometers away from their survey site. While passive control marks will continue to play an important role in the mapping community, making use of CORES and GPS allows you to keep up with this dynamic and changing world and start your survey almost anywhere.
In this part of the lecture series, we'll be tackling some computations that are found in the topic of the horizontal control network.
Adjustment of quadrilateral. We have here a sample problem related to adjustment of quadrilateral. The problem is, adjust the angles of the given quadrilateral. We have here the given interior angles, the small letter inside the table, as well as its corresponding values. We also have here the stations of quadrilateral, the station A, station B, station C, and station D. So we have here the solution. So the first adjustment, or the station adjustment. In this adjustment, we need to make sure that the sum of the angles about each station should be equal to 360 degrees. And if the sum of the angles, including the interior and exterior angle, is not equal to 360 degrees, correction is to be applied by determining the difference between the sum of the measured angles and 360 degrees. And the resulting difference is then divided by the number of angle about the station, and the correction is to be added or subtracted to each angle. So what we do in the station A, we will also be doing the same process in station B, station C, and also in the station D. So we have here the adjusted angles of the quadrilateral using the station adjustment. So next adjustment is the figure adjustment. So figure adjustment is only performed after station adjustment because it uses the values that is obtained in the first adjustment. So this adjustment requires that the sum of the angles for each triangle should be equal to 180 degrees. So in the process of adjustment, the three angles of each triangles are added together and their sum is subtracted from 180 degrees. And same as to station adjustment, the correction is to be added or subtracted to each angle. So we have here the adjusted angle. So applying the correction to triangle ABC, to triangle CDA, to triangle BCD, and to triangle DAB, we have here the adjusted interior angles of the quadrilateral using the figure adjustment. So next is the side condition. So in this, the sine of each angle should be proportional to the length of the opposite side of that triangle. So in here, we use the formula log sine of the angle plus 1 second minus the log sine of the angle. And we get the summation of the angles that uses the formula log sine of the angle plus 1 second, and also the sum of the angles that uses the formula log sine of the angle. So getting the sum 1 or the numerator by adding the angles A, C, E, and G, and also getting the sum 2 or the denominator by adding all the angles B, D, F, and H. So to compute the correction, we use the formula DE over the sum 1 plus sum 2. Here and here, we apply the correction to all the angles. And the sum of all the interior angles should be equal to 360 degrees.
Transit rule and compass rule. Here's our problem. From the field notes of closed traverse shown below, adjust the traverse using A. Transit rule, B. Compass rule, C. Compute the linear error of closure, D. Compute the relative error of precision. So in the table, our first column is the station occupied, the second column is our station observed, the third one is our bearing, and the fourth one is our distances. The first thing we will do is compute the latitude and departure using this formula. Latitude is equivalent to length multiplied to cosine and its bearing. So in our latitude AB, since it is due to north, our bearing is equivalent to 0 degree. So we just simply substitute the values, the length, and the bearing. In our departure, the formula to be used is length multiplied to sine bearing. So 400 sine 0 degrees equals to 0 meters. And here's our tabulated data. So we have here the total distances. RD is equivalent to 3,466.34 meters. The error of closure in latitude is equivalent to 1.01, and the error of closure in our departure is 1.7. Here is our solution in correction for latitude and departure using transit rule. So we have here our formula. Correction for latitude is equivalent to latitude multiply to closure of error all over the absolute value of summation of north latitude plus the absolute value of summation of south latitude. So CL over this summations of our north latitude and south latitude is constant. So we just get the value, which is 0.00523, and we will just multiply it to our latitudes. Same thing we did to our departure. Since CD or our closure of error in departure all over the absolute value of summation of east departure plus the absolute value of summation in west departure is constant, we just get the value and then multiply it to the departures. And we have here our values. And now adjusting latitude using transit rule. So we have the correction for latitude here in our third column. So in adjusting latitude, if it is from the north, you will subtract the correction, while if it is from the south, you will add the correction. So here is our adjusted latitude. In AB, our adjusted latitude is 399.79. In BC, we have 565.39. In CD, we have 350.18, negative 350.18. In DA, we have negative 564.11. In EA, we have negative 50.89, and it is equivalent to 0. So make sure that the total of the adjusted latitude will be 0. Adjusting departure using transit rule. Now that we have the correction for departure, we can now adjust our departure. So in our third column, we have here our correction for departure. Now, if we are going to adjust our departure using the correction, we will subtract the correction if it is from the east and add if it is from the west. So we have here our adjusted departure. AB is equals to 0, BC positive 565.28, CD positive 605.78, DE negative 205.36, EA negative 965.7, a total of 0. So we must keep in mind that the adjusted departure must be equal to 0. Here's the solution for the correction for latitude and departure using compass rule. So we have here our formula. Correction for latitude is equivalent to the area of closure in latitude multiplied to the distance all over the total distance. So we first find the value of CL over D since this is constant, and you can just store it to your calculator and multiply it to the distances of our station. So you can see it in our table below. So correction for departure, we have here our formula. Correction for departure is equals to the closure of error in departure multiplied to the distance all over D. So we first find the value of CD over D since these are constant, and you can just store it to your calculator, and then you can now multiply it to the distances of our station. So you can see the computation in the table down below. So adjusting latitude using compass rule. So now we have here the correction for latitude, and we can now adjust the latitude. So if the values of latitude are from the north, you will subtract the correction, and if the latitude is from the south, you will add the correction. So we have here the adjusted latitude of AB 399.88, BC 565.45, CD negative 350.20, DE negative 563.99, EA 51.14 with a total amount of 0. So you must keep in mind that the total of the adjusted latitude must be in 0. We have here the solution in adjusting departure using compass rule. Since now we have the correction for departure in our third column, we can now adjust the departure. If the departure is from the east, you will minus our correction, and if it is from the west, you will add the correction. So we have here the adjusted departure of AB negative 0.20, BC positive 565.29, CD positive 605.88, DE negative 205.50, EA negative 965.47, and the total of our adjusted departure is equivalent to 0. For our third problem, we are going to compute the linear error of closure. So we have here our formula. Linear error of closure is equivalent to the square root of the summation of error of closure in latitude squared plus summation of error of closure in departure squared. So we arrived at a value of 1.97740. For our last problem, we are going to compute the relative error of precision. So relative error is equivalent to the linear error of closure all over the total distance. So we have here 1 is over 1,753. It means that only 1 meter error is allowed for every 1,753 meter distance measured.
Strength of figure. We have here the figure of the quadrilateral ABCD with its station as well as its interior angles. We computed the number of geometric conditions to be satisfied in a given figure, or the C, by getting the sum of the angle conditions and the side conditions. we have the expression of the angle condition, which is n prime minus s prime plus 1, and the expression for side condition is n minus 2s plus 3, wherein n is the total number of lines in figure including the known line, the s is the total number of stations, the s prime is the number of occupied stations, and the n prime is the number of lines observed in both directions including the fixed or the known side of the given figure. We also computed the factor for computing the strength of the figure, and this is equal to d minus c over d, wherein d is the number of direction observed, forward and the back, and these not include the fixed or the known side of a given figure. Next, we determine the strength of figure for each chain of triangles. We have here the first possible route, the triangle BDC and ADB, having the common side BD. We can solve the triangle A and triangle B by computing the difference for 1 second that corresponds to the distance angle A and angle B of a triangle by following the formula log sine of the angle plus 1 second plus 10 subtracted to log sine of the angle plus 10. And after, we computed the R or the relative strength of figure by using the formula F or the factor for computing the strength of figure multiplied to the summation of values for the chain of triangles or the triangle A squared plus triangle A times triangle B plus triangle B squared. So we got 8.007102 for the relative strength of figure for triangle BDC and ADB, BD as the common side. So what we did for triangle BDC and ADB, BD as the common side, we will also do the same process for triangle CDA and DAB, DA as the common side. Also for the triangle CBD and CBA, BC as the common side, and as well as for triangle CDA and ACB, AC as the common side in determining the relative strength of figure. And therefore, for the possible routes, the strongest chain consists of triangle BDC and triangle ADB, BD as the common side, since it gives the lowest value of relative strength of figure. And the relative strength of the quadrilateral ABCD is 8.007102.
In this part of this lecture series, we'll be tackling about the spherical axis and how to compute it. So when the triangulation network has long sides, theoretically, it should be solved as a series of spherical triangles. To aid our understanding better, we have here a sample problem. The problem goes this way. The interior angles in a triangle XYZ are x is equal to 62 degrees, 20 minutes, and 10 seconds. Y is equals to 59 degrees, 50 minutes, and 30 seconds. And Z is equals to 57 degrees, 49 minutes, and 35 seconds. Side XY or side Z has a length of 35,820.65 meters. Assuming the average radius of the curvature to be 6,383.393 kilometers, compute the spherical axis and the corrected interior angles of the triangle. So in this problem, we are given the values of the interior angles, one side, which is side Z, and the radius. Those values are necessary for computing the spherical axis, but first, we will solve for the area. And to do that, we need to find the value of side X or the line segment YZ. To do that, we will be using sine law, which goes X over sine angle X is equals to Z over sine angle Z. Since we are only looking for X or the side X, we will derive the formula, and it would be X is equals to Z sine X over sine Z. Substitute the values, we would arrive at the angle or at the length of the side XYZ, which is 37,481.593 meters. Now we can solve for the area. So 1/2 of xy times yz sine angle y is the area. Substitute the values and we would arrive at the answer. Since we have now the area, we can now compute for the spherical axis. Using the formula, spherical axis is equals to area over r squared, the radius, sine 1 second. Substituting the values, we would arrive at the answer of 2.94 seconds. And the correction to be applied to the angles given is spherical axis divided by 3, which is the number of angles in a triangle. So that would give us 0.98 seconds. Since the spherical axis is a positive, that would mean too long, we need to subtract this correction to the given values. And with that, we would arrive to our corrected angles. Thank you for listening.
Vertical control network sample problem number 2. We have here the problem. Compute the difference in elevation between BM1 and BM2 if the backside reading of BM1 is 2.36 meter at an elevation of 153.2 meter above mean sea level, and the foresight reading of the same instrument set up to BM2 is 6.546 meter. So we have here the given, the backside of BM1 which is equals to 2.36, the foresight of BM2 which is 6.546, and the elevation of BM1 which is 153.2. So we are required to compute for the difference in elevation between BM1 and BM2. And here is the solution. Since the elevation of BM1 is already given, we have to solve the height of instrument by getting the sum of the elevation and the backside. And after that, we can then determine the elevation of BM2 by subtracting the height of the instrument to the foresight of the BM2. And to get the difference in elevation between BM1 and BM2, we just simply subtract their elevations. Vertical control network example problem number 3. We have here the problem. Lines of levels are run from benchmarks 1, 2, and 3 to establish elevation at junction 5. The number of setups per line is observed, and the observed elevation of junction 5 was also observed. We have here the given of the problem inside the table. For the first column, we have the routes, and for the second column, we have here the number of setups per route, and for the last column, we have the observed elevation in meters per route. So, in the problem, we are required to compute for the least square estimate for the elevation at junction 5. So, we have here the solution. First, we have to get the summation of the weight in every observations. The weights are inversely proportional to variances. So we compute the weights for us to determine the most probable value of the elevation at junction 5. Next, we compute the summation of the elevations multiplied by the weight of each observation. The weights that can be used to distribute correction depend on the number of setups. And lastly, to compute for the least square estimate for the elevation at junction 5, we simply use the formula, the summation of the elevations multiplied by the weights in each route over the summation of the weights in all of the observations. The
horizontal control network provided by two or more points in the ground, permanently or semi-permanently monumented and precisely fixed in position horizontally by distance and direction or coordinates. It is usually established by performing triangulation, trilateration, traversing, or by the use of GNSS or Global Navigation Satellite System. So when we say Global Navigation Satellite System, it is the standard generic term for satellite navigation systems that provide autonomous geospatial positioning with global coverage. The vertical control network provided by benchmarks in or near the track to be surveyed, and it becomes the basis for all elevations and in portraying the relief of the area. It is usually established by running lines of differential levels. GPS surveying may also be used, but elevations must be converted to orthometric heights first in order to be acceptable. Importance of standards. First, to provide a uniform set of standards specifying minimum acceptable accuracies of control survey for various purposes. Second, to establish specifications for instruments, field procedures, and misclosure checks to ensure that the intended level of accuracy is achieved. Factors affecting accuracy. First, type of condition of accuracy. Second, field procedure. And last, capabilities of survey personnel. In Article 7, Survey Accuracy, in Section 28, Survey Accuracy for Geodetic Control. It is said for the purpose of the said regulation or the revised regulations on land surveys, the control survey accuracy shall be as follows. In first order in accuracy, the relative error is 1 over 100,000, the linear error 1 cm per kilometer, nominal space 50 km, and vertical accuracy 4.80 mm multiplied by the square root of the distance. In second order, the relative error 1 over 50,000, the linear error 2 cm per kilometer, nominal space 25 km, vertical accuracy 8.40 mm multiplied by the square root of the distance. Third order, the relative error 1 over 20,000, linear error 5 cm per kilometer, and vertical accuracy 12.0 mm multiplied by the square root of the distance. The last order, fourth order, the relative error 1 over 10,000, linear error is 10 cm per kilometer. In designing network of controls, the intervisibility of stations are not necessary in order to have a good network geometry in the GNSS observations. However, in the preparation of the network design, it is necessary that the points selected can be occupied, located in a stable ground, and shall not be affected by any construction activities in the near future. Swampy or loose soil areas should be avoided. In map of the project site, the available NAMRIA topographic map on the area shall be used as base map. All the fixed controls or old control points, based on the available records, shall be platted. The points to be established shall be approximately platted on the selected locations. Caution shall be taken in order to scale the map correctly. The distance between points is an important factor. Each station shall be numbered properly. The network design's final map may be modified upon the conduct of field reconnaissance. Conditions on the network design. The lines connecting the control points within the network should create closed polygons with the minimum number of sides, such as triangles, that will create a rigid network. The network shall be designed so that all stations or points included therein have at least 3 known PRS-92 control points. The design network should have an adequate amount of redundancy. Optimal number of known points should be included. It as many cruise ties and repeated measurements as possible. And lastly, the field observations shall be timed when the position dilution of precision or PDOP is low. Horizontal control network and its method. Horizontal control network may be established by one of the following methods: traversing, triangulation, trilateration, GPS, and photogrammetry.
Traversing is typically used for smaller areas or areas with numerous obstacles. A traverse survey is used to calculate the distances and angles or courses between 2 points. So we have here the two types of traverse. We have here the closed traverse and open traverse.
Triangulation is a method of measuring angles on a network of triangles using a theodolite. The distance between control points is determined by the purpose and can range up to tens of kilometers. Trilateration is a simplified method of triangulation. The total time consumption of the process can be reduced in some cases, for example when using ADMI over long distance.
The Global Positioning System, or known as the GPS, is similar in some ways to the trilateration and EDM previously discussed, except that the known positions are now the GPS satellites and their orbits with 20,000 kilometers in space. The equipment and calculations are extremely complex, but for the user, the process is generally very simple. Photogrammetry, as its name implies, is a three-dimensional coordinate measuring technique that uses photographs as the fundamental medium for metrology or measurement. The fundamental principle used in photogrammetry is triangulation.
Vertical control network and its method. First is boning rods and travelers. A boning rod is made out of an upright pole with a horizontal board on top that forms a shaped rod. Second is side rail. A side rail consists of horizontal cruise space nailed to a single upright or pair of uprights driven into the ground. Third is slope rails or butterboards. These are used for controlling the side slopes in embankment and in cuttings. These consist of two vertical poles with a sloping board nailed near their top. The fourth is profile boards. These are similar to side rails but are used to define the corners or side of a building. A profile board is erected near each corner peak.
Good day! For this video, we will be tackling about the accepted standards of accuracy and specifications for geodetic control network establishment and operating geodetic control survey technology. And the reporters for this video are Charlene Joyce SAMSON,
Micaela B. CAGUICLA,
and John Patrick M. CASIO.
So first, we have the Article 7, Survey Accuracy, from the DENR Administrative Order Number 2007-29, the Revised Regulation on Land Survey. In Section 28, Control Surveys, for the purpose of this regulation and consistent with the adoption of new survey technologies, the control survey accuracy shall be as follows. So the accuracy, we have the first order, second order, third, and fourth order. The relative error for the first order is 1 over 100,000, for the second order is 1 over 50,000, for the third order is 1 over 20,000, and lastly for the fourth order is 1 over 10,000. The linear error for the first order is 1 cm per kilometer, for the second order is 2 cm per kilometer, the third order is 5 cm per kilometer, and for the fourth order is 10 cm per kilometer. For the nominal space in first order is 50 kilometers, for the second order is 25 kilometers, and the third order is 5 kilometers, and for the fourth order is indicated variable. The vertical accuracy for the first order is 4.8 mm multiplied by the square root of the distance, and for the second order is 8.4 mm multiplied by the square root of the distance, and the third order is 12 mm multiplied by the square root of the distance. In Section 29, Cadastral Surveys, the surveyor shall be guided by factors of efficiency and effectiveness in selecting the surveying methods and equipment in order to attain the following accuracies. So for the establishment of controls and political boundary survey, it shall be in accordance with the third order or the primary control accuracy requirement. And for the barangay boundary survey, it shall be in the fourth order or the secondary control accuracy. In lot survey accuracy, the standard accuracy of traverse closure shall be in accordance with the tertiary control survey requirement. So, in conducting isolated land surveys, the surveyor shall be guided by the following. For the original subdivision consolidation or consolidation subdivision isolated survey, it shall be conducted using equipment and methods that will meet the tertiary control accuracy. And when conducting relocation or verification survey, the allowable position of error shall not exceed a positive negative 10 centimeters. However, the allowable difference in the area shall not exceed a positive negative 1 square meter for every 1 hectare. In Section 31, for the mineral land surveys, survey of mineral lands executed for mineral agreement or for other purposes pursuant to the Mining Act of 1995 shall be in the fourth order of the secondary control accuracy.
Next, we have here Section 32 for Forest Land and National Park or the Protected Area Delimitation Survey, wherein the survey control accuracy shall be in accordance with the area coverage under the Project Control Survey, wherein the perimeter survey shall be undertaken in the same manner as in isolated survey. Next, we have the Section 10 Designing Network of Controls from the adoption of the Manual on Land Survey Procedures. The intervisibility of stations are not necessary or order to have a good network geometry in the GNSS observations. However, in the preparation of the network design, it is necessary that the points selected can be occupied, located in a stable ground, and shall not be affected by any construction activities in the near future. Swampy or loose soil areas should be avoided. Next, we have here from Section 12, the following shall apply in the preparations of the map of the project site. First is the available NAMRIA topographic map on the area shall be used as base map. And then next is all the fixed controls or the old control points based on the available records shall be plotted. Next is the point to be established shall be approximately plotted on the selected locations. Caution shall be taken in order to scale the map correctly, and then the distance between the points is an important factor. And then each station shall be numbered in accordance with Section 16 of this manual, and then the network design final map may be modified upon the conducted field reconnaissance. Next, we have here Section 13. Using the project site map, it shall be ascertained that the network design shall be made to conform to the following conditions. These conditions are: first is the lines connecting the control points within the network should create closed polygons with the minimum number of sides, such as triangles that will create a rigid network. Next is the network shall be designed so that all the stations or points included therein, it should have at least 3 unknown PRS 92 control point. And then the design network should have an adequate amount of redundancy or additional measurement over and beyond the absolute minimum required, considering that the main object is to have a required precision of the control point final coordinates, such as an optimal number of known points should be included, with as many cross ties and repeated measurements as possible. And then lastly, the schedule for the field observations shall also be included in the plan. The field observation shall be timed when the position dilution of precision or PDOP is low. A low PDOP value indicates a higher probability of accuracy.
Section 15. Geodetic Control Monument. The positions of reference points shall be defined and marked on the ground by the monument of permanent nature in the form of square-based frostum. Dimensions of survey control monuments. There are tables. Order of accuracy, top cross sections, bottom cross sections, length above ground, below ground. Concrete monuments shall be fabricated with reinforced steel bar by 10 mm in the diameter for vertical bars and 8 mm diameter of that for ties, and satisfying the requirements of Class A concrete specifications in the ratio of 1 to 4, or translated into a concrete mixture such as 1 cubic meter of cement and 2 cubic meters of sand and 4 cubic meters of gravel or bags of cement, 4 bags of sand, and 8 bags of gray gravel. Sands of gravel must be clean, free from dust and mud or organic matter. C. Concrete monuments shall be cast into place where they will be established. So there are illustration where CGY is the provincial code, Cagayan 3000 in a control point number, 2005 is the year when monument is established. So triangle is a control point mark embedded at the center of triangle. Second order is the order of accuracy. The monuments LMS2 is the office of entity established by reference point. Section 16. Markings of reference monuments. They shall be marked on the top with engraved letters and shall consist of 5 parts, namely provincial code, control point number, year established, order of accuracy, and of office or entity that establish the reference monument. A. The list of provinces and their corresponding code is found by Annex 4 of Manual. The number shall be consulted for assignment for code to the newly created provinces. B. The numbering control points shall be formed into 1 to 3,000 for those established by Numberia and 300, and so forth for those established by LMB, for LMS, and other entities. C. The number of office or entity established by control point shall be inscribed using only one word, which could either be acronym, company name, or surname of a person. D. To avoid duplication of numbers, the established entity shall coordinate with Numberia for first and second order control points with the concrete LMS regional office for the third and fourth order control points. The LMS shall be furnished the data to LMB and the established control for the updating of reference point national database. E. Letters and numbers shall be Arial bold, font type, all capital, and shall be 2 cm height, 2 cm width, and 0 cm thickness with margins not less than 2 cm along the edge of monuments to give allowance for chipping. F. Shall bear the mark GovProp, which stand for government property. So there is an annex of province code. Section 19. The establishment of geodetic control covering for the first and second order accuracy shall be done by only GNSS receiver. There shall be less 3 receivers units per survey team. The employment of more than 4 receivers is preferable. Section 25. Connection for exciting controls. The connections shall be made to control of same or higher order of accuracy following numbers of observation. So there are table to archive, minimum observation, recommended observation. For the first order, 3 of minimum observations and 4 or more for recommended observation. For first order is 2 for minimum observation and 3 or more recommended observation. For the last, 2 for minimum observations and 2 for recommended observation. that's all.